I wanted to share my interest in mathematical conjecture generation. Instead of solving any real problems, I'm looking to pose some new ones. I'll mostly talk about this work we did a couple of years ago. You can read about it if you want technical details about the paper, but during the course of the talk, if you have a question, please feel free to stop me and ask. I want to begin with a story. So in the year 1900, at the International Congress of Mathematics in Paris, David Hilbert proposed a number of conjectures or open problems. And a couple of them might have been solved in the same year itself, but we don't really talk about them. In the 20s, he sort of goes back to and talks about the unresolved problems, and he writes this 8-page document, 5 of which was devoted to this 13th problem. So what is the 13th problem? So Hilbert proposed the following question. So if you have a degree 7 polynomial in one variable, by techniques known at that time, you could show that it is reducible to this form. The question Hilbert posed is, can you write down the solution to this equation, not only as a function of a, b, and c, the unspecified coefficients, but in a very specific form? He demanded the solution be expressible as a composition of finite number of 2-variable functions. So this was the 13th problem that was posed in 1900. Now, fast forward 50 years, Soviet mathematicians Kolmogorov and Arnaud, they came across this conjecture, and Kolmogorov and Arnaud had a supervisor-supervisee relationship. Arnaud was only 19 years old at that time, and they sort of betted against each other. They said, one said that Hilbert was incorrect, and the other said that no, he was correct. As usual, the supervisor won, and the result that resolved Hilbert's 13th problem, at least partially for continuous functions, resulted in this mathematical supernova known as the Kolmogorov-Arnold representation. So what is interesting about this representation is on the left-hand side of this equation, f of x, where x is a real valued vector, and f is any continuous function that takes a bunch of real numbers and gives you one real number. So what Kolmogorov and Arnaud managed to show is you can always write down any continuous multivariate real valued function in this very specific form. Now, if you look at the right-hand side of this expression, you see something quite funny. There are a bunch of functions, these phi's with 1 or 2 indices. However, the function in the interior, in the second summand, accepts only one variable as an input. So what this is really saying is the only true multivariate function in the real domain is the sum function. Now, this is rather interesting because the result doesn't really generalize to complex functions. Actually, I don't know, perhaps some of you might know to what class of complex functions might this result generalize to, but as far as I know, that's an open problem. This representation theorem was polished by a number of others, and there are various ways of expressing this result. But one interpretation of this representation theorem, due to its compositional nature, yes? Due to the compositional nature of this representation, in the 80s, computer scientist Robert Heck Nielsen, who came across this result, realized that, wait a minute, this compositional form merits a neural network architecture. But it's quite different from the neural architectures that we are used to in the context of deep learning. In that, we know for a fact now that due to various guarantees from analysis, known as universal approximation theorems, that we can model any reasonably well-behaved function through these neural networks. However, if you actually build the neural network dictated by this representation, you realize that those neural networks are actually exact. They are not an approximation. So what's really going on? So Heck-Nielsen further explored the interpretation of some of the functions that appear in this representation, and sort of indicated that you can attempt to understand some of the functions here as activations inside this neural network, which he built and called Kolmogorov mapping networks. Now, the activations can be interpreted as generators of space-filling curves, something that is quite non-smooth. And so if you try to use these neural networks in your favorite task, for example, playing the next song in Spotify, you may struggle. But this representation actually allows you to explain why deep learning actually works. By adding additional layers, what you're doing is controlling the behavior of these weirdly behaving activation functions. So this is an explanation of why neurocomputing is on solid mathematical footing. Why should we use neural networks? So now, jumping back to Hilbert's 13th conjecture, within this period of 8 decades or so, you sort of started with a question before computers even existed, and you ended up in a setting where you are able to explain why these neural architectures of today can actually work. So this begs the question, what is a good conjecture? So what is a good conjecture is actually extremely hard to define because there might be many subjective components to it. If a problem has been open for, let's say 150 years or so, you might claim that, oh, okay, perhaps this is a good conjecture because of our inability collectively to solve or resolve these questions. But good conjectures do share certain commonalities, although we may not be immediately able to define the characteristics of a good conjecture. So fellow string theorist Robert Digraph wrote this beautiful article, which I encourage all of you to read, called The Subtle Art of Making a Conjecture. And he noted down some common properties that good conjectures might satisfy. First of all, they must be non-trivial. I mean, 1 greater than 0, lovely as it sounds, is rather trivial. There must be some amount of evidence in favor of it. Now, we know a bunch of problems across mathematics where we have tons and tons of evidence in favor of mathematical conjectures, yet we have been unable to resolve them. So one property that we definitely must require is that there must be substantial evidence in favor of it, especially in situations where that evidence is actually easy to calculate or compute. Now, putting on the physicist's hat, a good conjecture might look nice, might have a terse representation. This is sort of effectively saying that we believe in Occam's razor. We want simple explanations to mathematical phenomena. When John Conway was asked about what is a good conjecture, in classic Conway style, he said that a good conjecture must be outrageous. So Digraph also notes that if a conjecture is proved within a few months, then perhaps its creator should have pondered it a bit longer before announcing it to the world. A sagely advice that I'll ignore for the rest of this talk. So let's consider a class of conjectures. So when I first started working on this, it seemed easy to work with algebraic things because you can compute things. And perhaps there are some techniques from invariant theory and other branches of mathematics that might actually become useful in this very algebraic setting. Inequalities are abundant in mathematics, and there are wide-ranging applications for inequalities. For example, you can bound functions. For example, if you consider some number theoretic functions, you might be interested in upper bounding or lower bounding them for various reasons. If you are working in analysis, you might have similar requirements, and some of the most powerful results often take this form. I should also comment that there's this very wonderful book which is a compilation of inequalities done by Hardy-Littlewood and Polya almost a century ago. And for no apparent reason, well, at least not apparent to me, all inequalities that were known at that time were compiled or attempted to be compiled in this book. And Hardy-Littlewood and Polya also note that we have almost always found, even with the most famous inequalities, that we have a little new to add. So to state my goal at this point, we want to build an oracle, if you will, that interacts with human mathematicians to generate novel conjectures about inequalities for which we have a substantial amount of evidence. Now, a little poll, just to give an example of an inequality conjecture. I've written down a couple of lines below the inequality, generic inequality f less than g, where I'll note that sigma of n is the sum of divisors function, and h of n is the nth harmonic number, and gamma is the Euler-Mascheroni constant. Can somebody guess what these inequalities represent? It's the sum of divisors of n. Hint, they are equivalent to each other, although I have not specified the domain. The domains are slightly off. Yeah, correct. So it's fascinating that a conjecture as deep as the Riemann hypothesis also admits an inequality representation. I'll also point out that there are 3 volumes of books of alternate formulations of Riemann hypothesis. So this is also a sign of a deep conjecture in that it talks to many different kinds of mathematics. So I'm looking at inequalities, but what if we considered all possible inequalities between continuous functions? How can we organize them? Does it form a reasonably well-defined space? And if so, what properties does this space have? Emmy Noether is my personal hero because she did fascinating and groundbreaking work on invariant theory more than, well, almost 100 years ago. And again, putting on my theoretical physicist hat, symmetries are kind of everything in modern theoretical physics. If you, for example, take Newton's second law, in the absence of any external force, the rate of change of momentum is 0. What it's effectively saying is you have translation symmetry in nature. If you look at nuclear physics, we have gate symmetries which describe the invariance you need to write down your action or your quantum field theory. If you look at Einstein's relativity, special relativity effectively is a consequence of Poincare invariance. General relativity can be understood to be a theory that is invariant under general diffeomorphisms, and so on. So symmetries are a very powerful tool that physicists have successfully utilized in their theoretical endeavors. So let's make a definition. So let's take 2 continuous real-valued multivariate functions defined over a compact domain D. And we're going to define 2 spaces, R and C. R, I'm going to call the space of relations, which is effectively a tuple of continuous functions with no special properties. But inside this, embedded inside this, is something I'll define to be the conjecture space, denoted by C, where F is most definitely less than G at all points. So in the space of relations, you have a pair of functions with no special properties, but as soon as you get inside this space C, or the conjecture space, you start seeing relations between F and G. Now, very inappropriately, I actually do not know what the conjecture space should look like. In fact, it's a infinite dimensional Banach manifold. So I borrowed this projection of a Calabi-Yau manifold to represent the space, just a hangover from string theory. Note that the point 0, 0 is in the space of relations, but actually not in the space of conjectures, because 0 is not less than 0. So again, in our desire to be guided by symmetries, we pose a couple of group theoretical questions. Now, formally, we show that R is a Banach space and C is a Banach manifold. And typically, Banach manifolds can turn out to be really ugly objects, or it might have a lot of structure in it. Turns out our situation is the latter. So we ask the question, what is the largest group acting linearly on C? And are there any free group actions on this space? Now, one of the advantages of characterizing symmetries of this space is down the line, when we implement or implemented machine learning on this space, it's actually quite useful to be cognizant of the symmetries, because it effectively reduces your search space by a factor which is related to the order of the group. So we started with our symmetry classification of this space some time ago, and there have been some new developments, but I'll tell you some of the core results that we are most excited by. So one of the first things we found is that if you act on the pair f comma g by these GL matrices, you find that it sort of keeps you in the space. And we also found that that some of the largest possible groups that you can have in this space might be related to this representation of symmetries. So we sort of realized that you can always write down this group of isometries in the form denoted by A. So we effectively show that this is a 3-parameter Lie group that acts on this space. And it can always be decomposed into two things. One is a group of dilations, which sort of scales your mathematical inequalities. And the other is not as easy to explain, but actually quite simple if you look at the underlying mathematics. So we also attempt to address the following question, that does this group or any subgroup of it act freely on this? If a subgroup acts freely on this, then perhaps we can take quotients and simplify our computational exercises down the line. So we found that there are a number of subgroups that do act freely on this space, and we characterize them, and we show that they are also matrix Lie groups, and a full description of them is accessible in the article. So what do we really want to do here? We want to discover inequalities that live on this space that are hard to resolve. But computationally, what is the process that we follow? We sort of randomly initialize on the space of relations, and we wish to navigate ourselves to the space of conjectures. As soon as we hit the space, we can read out a mathematical inequality. If we understand the symmetries, we immediately have infinitely many other inequalities under the group orbit. And the algorithm that we have employed is rather simple. It's just gradient descent. And the objective that we optimize over is related to the signum function. So effectively, the kind of symmetries we end up discovering, they talk to the loss function through this signum function. So what we're saying is, if we have two continuous functions, and let's say their difference is never allowed to cross 0, then the kind of symmetries that will preserve this property will also preserve the signum function of the difference of the two functions. So effectively, we are attempting to solve a sampling problem. So what do we find? We have not introduced any novel measures of interestingness on this space, and these are things that we think about. But some of the initial runs is what's on the screen. So in this slide, pi is the prime counting function. And of course, you can prime counting function is normally defined perhaps over integers, but it's easy to extend it to any positive real number. And one of the first things we found was number 5, which basically shows the subadditivity of the prime counting function. And turns out, approximately 100 years ago, this was noted in the maths community as Hardy-Littlewood's second conjecture, which is still not resolved. So we were quite surprised that actually we can, just by introducing certain interesting functions into our function box, and enforcing that there is agreement on a certain amount of data, we actually retrieve certain non-trivial results. In fact, the amount of data you require to produce conjectures is a function of the kind of mathematics you're looking at. So for many number theoretic functions, we find that actually you only need a few data points. You need like 10 or 20 or 40 evaluations of this function to come up with the conclusion that, hey, this conjecture might be true. We also find a bunch of other things. Here's a trivial theorem that we found, which is number 1. I think any mathematician might agree with this result, although we have still not been able to fully prove it. We only prove a case of this. I apologize. I don't think you can actually see the conjectures here. But if I zoomed in, perhaps you'll appreciate that there's you can go crazy with generating conjectures about the prime counting function alone. Right. So one of the conjectures we found was pi of a times b is greater than or equal to pi of a plus pi of b. And not being an expert in number theory myself, I immediately struggled to prove this until I spoke with some mathematicians, and they pointed out that, oh, you might want to look at the Rosser-Schonfeld formula or the inequality. And that immediately allowed us to prove this result. Later, we have also experimented with LLMs and thrown this thing at them and asked the LLM that, hey, can you prove this? And it turns out that, oh, maybe it takes some significant steps, but it does need some nudges. On the top left of this slide, you'll see that there's a short table where we sort of, we propose some conjectures about the diameter of Cayley graphs of non-abelian simple groups. And there's a very famous conjecture by Laszlo Babai from '92, which says that the diameter of the Cayley graph of any non-abelian simple group with a symmetric generating set is upper bounded by a very simple looking function, which is the log of the size of the group raised to the power c. Now I'm given to understand that c might be equal to 2, but as far as I understand, that's not established completely. So we were quite interested in understanding can we frame conjectures about finite simple groups, or rather the diameters of the Cayley graphs, in terms of quantities that we might use in computational settings, such as the order of the group elements or traces of matrices that represent these generators. And we found that you can write down neat conjectures as well as rather ugly looking conjectures, as number 4 exemplifies. Now, motivated by some of these thoughts, we wrote this short paper called "Learning to be Simple," where we find that there must be certain necessary conditions that these generators must satisfy, and no pun intended for the title of the paper. Now, this is really fun, generating conjectures with this simple algorithm. So why stop at the prime counting function? You can have fun with various arithmetic functions or your favorite part of mathematics. And there's endless amounts of conjecturing you could be doing that are of this inequality form. And the table shows certain examples. So number one is quite interesting because it's the Mertens conjecture, which is now disproved. But here's the weakness of what we are doing. If you have a counterexample to your theorem, which is not readily accessible, then you're going to propose this false conjecture. So this is a weakness of this paradigm, mainly because we are not attempting to prove anything here. All right. So let me talk a bit about some other formal properties of the conjecture space. So over the course of the last year or so, we have sort of simplified our formalism, and the biggest change is F minus G is now denoted as H. So we now redefine the space of conjectures to be any continuous function that either lives above zero or below zero. And we find a much larger group action on this space. And the group action is described by homeomorphisms of R star. Now, R star, because your function or your conjecture in this case is never allowed to assume the value zero. So if you have bijections that transform one of your inequalities to another, then you're golden. We have also found certain other properties of this space which are quite surprising or unsurprising, depending on your point of view. We found that if you multiply positive or negative functions together, you're of course going to get always positive or always negative functions. So the space itself admits a group structure under pointwise multiplication. The more non-trivial group action is due to this homeo R star denoted by G here. And we show that under this group action, where the group operation is composition of functions, you also get a group structure. Yes, thanks for that question. Yes, so the space itself is a function of the compact domain you might have you might have picked at the beginning. Yeah. So some further explorations about the conjecture space. So very recently, we found that this rather surprising result where we focus on the positive part of the space. Namely, we look at we only look at continuous functions that are always positive. And one connection to the to complex numbers is that one of the group actions that acts on the complex upper half plane is the SL2 action. And that action effectively preserves the imaginary part of the complex number. So we find this rather surprising result, which I noted below. C greater is the space of all positive continuous functions. And we believe the following must be true, that you can express this space as a double union, where you are effectively borrowing one function from your space of relations, coupling it with a positive function, and you can find an infinite source of other positive functions guaranteed by the SL2 action, where you imagine the real part of the complex plane as denoted by F, which can take any value, and the imaginary axis is denoted by is represented by the function G. Right. So conjecture space is just a simple geometric object on which a lot of interesting mathematical inequalities live. And the task of generating a new conjecture in this space is equivalent to is equivalent to sampling from this space. Now, perhaps we believe in the interconnectedness of mathematics, and this should be on display completely in the conjecture space in the following sense. So, for example, if you no longer believe one of the inequalities to be which are actually true on the space, then it will have a knock-on effect on the entire space. And the way to study this that we have considered in the future is through bootstrapping techniques by figuring out what the symmetries of the space might be, and considering their invariance, and checking whether these allow us to generate non-trivial conjectures of the inequality type. Now, there's a number of connections to various other paradigms of finding mathematical conjectures. One particular one is something we heard about in the last talk by Fernando. If you consider two functions, f and g, here's an idempotent operator that might be interesting. Let's take the maximum, pointwise maximum of two functions, f and g. This is an idempotent operation that might allow this space to have the structure of an algebraic semilattice. You can also consider relations between different mathematical inequalities. For instance, the two versions of the Riemann hypothesis that were shown earlier. One is Robin's formulation of Ramanujan's formulation of Riemann hypothesis, and the other is Lagarius's formulation of Riemann hypothesis. Now, you may choose to draw an arrow between these two inequalities on this space with two directions. So you can study implications of one inequality vis-a-vis another by drawing a causal graph. And these are some of the frameworks we are exploring. Now, there are various representations to consider here. Typically, we start with a function box of our favorite functions, and we simply run gradient descent and optimize over this loss. And if we manage to divert the attention of or bias our optimization towards finding more interesting things, then perhaps those are the outcomes that we want. We want to find more conjectures like Hardy-Littlewood's conjecture or the Riemann hypothesis, as opposed to trivial conjectures, which would be definitely true on a huge amount of data. Perhaps commented already on the kind of applications that one might have due to finding inequality type conjectures, and there are a number of things we have explored. We have explored conjectures about random matrices, conjectures about graph theoretic quantities, conjectures about numerous other things. One of the applications that we have been looking at is to look for holographic entropic inequalities, which is something that appears in physics, and those are also examples where we were able to find certain new inequalities. So that's sort of the kind of the end of my talk, but I'll also speak a little bit about a couple of other things that relates to this thing we are building. More collaboration is more science, right? So one of the things we've been doing is with intern Yuka Machino. She went to the International Maths Olympiad, which was in Bath last year, and she did a survey of interestingness of mathematical conjectures amongst the participants. And this is the first time we have had to apply for ethics approval on mathematical research, because you're supposed to do that when talking to participants at IMO who might not be 18. There are certain other conjectures which we look at with experts. So, for example, the ABC conjecture is an example of things we look at with Min Hyung Kim, who is an expert in Diophantine geometry. There's also some applications of conjectures for mathematics education that we look at with some folks in Cambridge. And they are a combination of mathematical experts or machine learning experts and also experts in maths education. I'll finally finish with and open up to questions and discussions we can have by pointing out some other work involving machine learning on our quest to finding Ricci flat metrics on string theoretic settings. So this is a very interesting conjecture. So in the 60s, Eugenio Calabi described that manifolds with certain holonomies admit a metric that are flat, that is, they have zero curvature. Now, after several years of attempting to disprove that conjecture, Xintung Yao ended up proving it. And the proof is an existence proof, which doesn't really help the string model builders. And in fact, Yao says that no matter whichever way he attempted to disprove the Calabi conjecture, his attempts always seem to fail in a very subtle way. And so nonetheless, some years ago, we started some machine learning explorations on this problem by creating some neural representations for the metric that we wish to find on this space. And it's a large collaborative work spanning various institutes in the States and also IST Lisbon. Damien, who's in the audience, is one of the key contributors to this. So here what we do is we create a neural representation, and we attempt to find parameters of this neural representation that actually satisfies Einstein's field equations in vacuum. And turns out that if you follow this procedure, you're effectively doing something like physics-inspired neural networks. You're trying to find the right parameters of your approximate metric such that the Einstein's field equations are satisfied. And if you're accurate enough, then you might get a glimpse at the formulaic form, if it even exists, of this missing Ricci flat metric. So building on these neural representations, one of my students, Victor Mirjanic, he sort of treated the neural network as a black box and ran symbolic regression on this. And what we found is rather interesting. We found that in very simple settings, you can actually extract out some analytic formula which are almost as good as an approximation to these vast neural network architectures with tens of thousands of parameters, whereas the formula that we extracted have only a handful of parameters. We also find that you can actually fully describe the metric on some subloci of this space. Right. Any questions? All right. Oh, sorry, go. I can talk about this slide for an hour, but so far I should. All right. I promise this is my last slide. I already described how neurocomputing can be thought of, how the mathematical foundations for neurocomputing can be thought of as this representation theorem that Kolmogorov and Arno came up with. There's a number of interesting lenses through which you can look at neural networks. One result that I like pointing out to various people is this interesting paper that appeared a few years ago on tropical geometry of deep neural networks. And it sort of goes as follows, that in the tropical geometry setting, you define two different, you define addition and multiplication quite differently. You define addition as taking the maximum and multiplication as addition. And if you imagine now constructing polynomials using these operations, you will only obtain piecewise linear functions. So therefore, the class of tropical geometries that are described by hypersurfaces are in one-to-one correspondence with certain types of neural networks. So if you're a geometer and want to be excited about neural networks, here's a mathematical lens for you to look at. There's also this triangular connection between Ricci flow, RG flow, and how a neural network might train, which is something that some machine learners and theorists have looked at in the past. Let me describe this very quickly. So in the neural network setting, we typically use some form of optimization to get to the right set of parameters. Now, this is sort of Euclidean. However, you can choose to put a metric or a Riemannian metric even on the space of neural networks and do geometric gradient descent instead. Now, this procedure is very analogous, I believe, to Ricci flow or RG flow, which are much better understood in the mathematics or geometry or physics communities. So this triangular connection is also something that provides another lens to view neural networks. So I'm going to stop here. Thank you for your patience.
Thank you very much for this very nice talk, really. Are there any questions?
I had a question about the last slide, literally the Ricci flow, RG flow, and the neural network training. Do you have a fixed point for the weights? Is there an IR fixed point for the weights that does the neural network evolve to a fixed point? Is that what happens here?
We don't really know. We believe that the dynamics of training is analogous to some modified version of Ricci flow called Ricci-de-Turck flow. So if you put a Riemannian metric on the parameter space of the neural networks, which is only slightly different from a flat metric, then you notice that the way the metric itself evolves over time results in a parabolic differential equation, which is a close cousin of Ricci flow, known as Ricci-de-Turck flow. So I don't know if there are fixed points.
Okay, and you can't do this, for example, for the Kalan-Zemanzik equation in FIFO theory, in field theory?
One might be able to do this.
Okay, thanks.
But I don't know.